Okay, a couple announcements. You have your exam 2 that opens today after class. It's in zip grade. It will be open for 24 hours. Make sure you hit the like, subscribe, and submit button on that so your points get recorded. It'll close tomorrow at 2:15. Your interim grades have been calculated, submitted to SOAR, so that's ready for your advisement. Your module points have been updated in Canvas, and your rank and Z-scores as well. So remember that primarily you're earning points through the exams this semester. Exam 2 has 30 questions and 9 bonus questions. Any questions, comments before we get started? Okay, so we have a lot to get through today. We're finishing up the amines on oxidation state 1. And then on Wednesday, we'll start oxidation states 2 and 3. So we're all building on these functional groups. You'll see a little bit of oxidation state 3 stuff today when we start learning the reactions of amines. To start off with, we're going to continue on this discussion of the structure of amines, really about where the lone pair on a nitrogen atom is located. And that deals with figuring out the basicity of nitrogen. So remember, the action of a base is to abstract a proton, and so the lone pair has to be available to do that. So we recall that nitrogen, typically in the neutral state, has 3 sigma bonds and 1 lone pair, and the lone pair is what will act as a base. But we have these other bonding patterns, as we'll see in the molecules when we talk about them, where we have to figure out what's the hybridization of the nitrogen, where does the lone pair reside. So we have a couple compounds here, imidazole, caffeine, and nicotine. So you can see the blue N indicates nitrogen, but the bonding patterns vary from each of these molecules due to the different functional groups. So within all of them, you can see that the nitrogen does show 3 bonds, but what about the lone pair? So imidazole is a 5-membered nitrogen heterocycle. The reason we're talking about this, it's the side chain in histidine, which is an amino acid, and we'll talk more about that in Module 5. But when you look at those 2 nitrogens, what's the hybridization of the one on the left? So sp2. And we can tell that by looking at number of sigma bonds, number of pi bonds. And then what about the nitrogen on the right? So it looks sp3, but it's sp2. So if we accept the fact that imidazole is an aromatic compound, the nitrogen has to be sp2 so that the electrons in the p orbital can be delocalized throughout the ring. So if I draw that lone, I'm going to draw that lone pair outside the ring. This is how I remember this. And then I'm going to draw this lone pair inside the ring. So the question is, where does that lone pair reside in each? So for the nitrogen on the left, the lone pair is in an sp2 hybrid orbital. So So sp2 is trigonal planar. That electron pair is in an sp2 hybrid orbital. For the one on the right, we're showing 3 sigma bonds. So the lone pair has to be in a p orbital. And that will allow it to achieve conjugation with those pi bonds. So for the nitrogen on the left, because it resides in an sp2 hybrid orbital, it's not involved in conjugation. And we further know that because, see that pi bond there? The N and the C are sharing p orbitals to form that pi bond. That means the 1 electron from nitrogen is going into that p orbital. It's forming the pi bond with the p orbital of the carbon electron, and that's how you get that pi bond. So you really have to understand the nuance or minutia of that in terms of what is a basic nitrogen. If we go over to caffeine, you can see the substructure of a imidazole embedded in there. So there's the 5-membered ring of imidazole, and then you can see it over here. But then you also have this other heterocycle with these 2 nitrogens. So on these 2, let's put the lone pairs in there. Those nitrogens are also sp2 hybridized. And the reason for that is because the nitrogen lone pairs will delocalize through resonance onto the oxygen. Now, amides are really the only ones that do that to the greatest extent. And a consequence of that is, again, when we get into module 5, that's what proteins are made of, these long amide chains. And that amide bond, which is called a peptide bond, is the strongest of that functional group type. So sp2, 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 sp2. So now in nicotine, we have a 6-membered ring. That's called pyridine, and then this 5-membered ring called pyrrolidine. You can see the nitrogen atom is showing 1, 2 sigma bonds and a pi bond. So the lone pair here, I'm going to draw outside the ring. That means it resides in an sp2 hybrid orbital. The other nitrogen in the 5-membered ring, now that's a true sp3 hybridized nitrogen. So the difference between this 5-membered ring and the nicotine versus imidazole, notice that this one has no double bonds. So that nitrogen is sp3. Questions? So again, the location of that lone pair is going to help us understand how basic the nitrogen is. And I know we talked about imidazole, but if we remove that second nitrogen, we have pyrrole. And so that lone pair is shown with the orbitals, is in a p orbital. And it's like that because it can be delocalized through the pi bond. In pyridine, the lone pair is in an sp2 hybrid orbital. And so you see here it just sticks out. It's not involved in conjugation. So in that case, for pyrrole, because the lone pair is delocalized, it's not a very good base. Whereas in pyridine, it's sticking out orthogonal to the pi cloud. And so now it's a better base. It's more available to abstract a proton. So in terms of nitrogen hybridization, the trend is sp3 is greater than sp2 is greater than sp. And again, the reason for that is for an sp3 hybridized nitrogen, the lone pair is in an sp3 orbital, and so it can abstract hydrogens readily.
Is that hybridization trend referring to the nitrogen atom itself or the lone pair?
Both. So that's the two things you have to consider is like looking at the nitrogen, determining the hybridization, and then figuring out where the lone pair is going to reside. Because again, the issue is pyrrole versus pyridine, how that lone pair, if it's in the p orbital versus the sp2 hybridized orbital. So I always find this concept, I have to calibrate myself on nitrogen basicity because we're using the acidity scale. So we're starting with a protonated nitrogen, and then we're normalizing it to the pKa scale that we're familiar with from organic 1. But remember, there's an inverse between acidity and basicity. So what we figure out from this scale, you just sort of in your mind flip it, and that helps you rank amine bases. So for this species here, we have a nitrogen with a positive charge, so that's ammonium. And then we have this equilibrium expression in water, where we do a proton transfer from the water, basically abstracting one of those hydrogens. And then we get the amine, and then we get hydronium. So from this argument, we're able to figure out the basicity using that inverse relationship. So the Ka expression, as we learned in general chemistry, you have the product of the concentrations of the products divided by basically that of the reactant. Since water has a fixed molarity, it just gets folded back into the Ka part of that equation. That's why you don't see it in the denominator. So again, it's normalized to the pKa scale. We're going to look at those pKa values, but in our mind, sort of flip the trend because we're talking about basicity. So from that Ka function, we apply the logarithmic operation. So there's the negative log that turns it into the pKa. And that's the numbers you see in red. So remember that the lower that number, the more acidic. So negative 10 is the most acidic, 10.75 is the least acidic. And so above it, we can talk about basicity. So more acidic would mean weaker base. Least acidic would be stronger base. And so keep in mind when we say base, what we're really talking about is the starting amine. So overall in this trend, as we can see, the structure, the three structures on the right, those carbons are all sp3 hybridized. So those are stronger bases. So imagine above here the neutral compounds. Those bases are all stronger than the sp2, than the sp. So meaning if we wanted to use an amine in an acid-base reaction, we would choose something that's sp3 hybridized to do the proton transfer. So these are stronger bases. And then on the left side, these are stronger acids. So again, that trend is summarized here. So why do we use amine bases? You know, when things like sodium hydroxide or potassium carbonate or these inorganic bases are readily available. Well, since they're inorganic, they're not really soluble in organic solvents. So we need organic bases, and the nitrogen is the best functional group for that. So it comes down to really solubility issues. So think of all the solvents we've learned about, like non-polar, like hexanes, a little bit polar, like diethyl ether, dichloromethane. You cannot get sodium hydroxide solubilized in those. So we use these amine bases, you get one phase, and then you can get your reaction to go. So I think for this one we already answered, but let's just go through it to review. Again, we have imidazole. We have two sp2 hybridized nitrogens, and it says in what orbital type do the lone pairs reside? So I was going to put these on the outside, meaning that they reside in an sp2 hybrid orbital. These on the inside, sort of to indicate aromaticity. And so that's residing in a p orbital, and then we would get B. So with imidazole, if you use it as a base, that's the nitrogen that gets protonated. Has anyone taken biology, biochemistry, anything like that yet? I've heard of the catalytic triad. Sounds like some mafia group or something, but when in enzymatic reactions, you have these amino acids. And so typically there's like 3 of them involved. Histidine, which contains imidazole, is one of them. So in enzyme pocket, that histidine nitrogen helps shuffle protons around between amino acids and the substrate that goes in there. So this one was one, so more basic. again, due to the lone pair being in the sp2 hybrid orbital. So with molecules that have more than one nitrogen, I typically refer to them sort of in this way as like a pyridine type nitrogen or a pyrrolidine type nitrogen. So the pyridine, that lone pair is in an sp2 hybrid orbital. So that eliminates C and D. The pyrrolidine, that's just a straight sp3 hybridized N group, so the lone pair has to be in an sp3 orbital. So that would eliminate B, and we would end up with A. Don't want to jump the gun here. Any questions on that? So the next question is, of those two, which one is more basic? So sp2, sp3, that really helps us answer the question. So it's the pyrrolidine type that's more basic. So what does all this mean? Again, nicotine has two nitrogens. If you treated it with one equivalent of HCl, that's the acid, which one gets protonated? It's going to be this nitrogen right there, because that lone pair is more available. So that gets protonated, the N gets plus, and then we balance it with Cl minus. So that's a salt. Typically, when you think of salts, you think of solids. And in the pharmaceutical industry, if you take a prescription drug, more likely than not, it's probably a salt. That helps with creating it, and then usually with how it's absorbed in your body, because now it's ionic. You know, when you take a pill, it gets into your gut. You know, that's aqueous conditions. It helps basically metabolize it. Any questions? Okay, so there's histidine. That's an amino acid. So we have an acid. Primary amine, and a side chain. So all amino acids have that. Basically, what differs in them is what is the nature of the side chain. This carbon right here, next to the carbonyl, is called the alpha carbon. And it says which nitrogen in histidine is the most basic. We just categorize them. That's sp3, sp2, sp2. And so from our trend, we know that the sp3 is going to be the winner. So you may have already seen this in some of your classes, but when we learn about making biopolymers of amino acids, The side chain will determine the polarity of the molecule. When you treat it under acidic or basic conditions, you do a titration. Everyone's favorite activity from general chemistry. Forget to add the indicator. You add all your acid and base, the color never changes. I'm sure one of you has done that. The charge on that chain is important in terms of how it then folds up, which gives it its activity. So the message here is if you know these important structural features, you're able to better understand how these things act in the body. So what about caffeine? We already said that all of the nitrogens are sp2 hybridized. But then sp2 is the weird one, whether it resides in the sp2 orbital or the p orbital. And that's when you're just looking at the bonding pattern. So for this one, in the imidazole part, I'm going to say that resides in the ring. So that's p orbital like. This is outside the ring. That's sp2. Now these other lone pairs basically get delocalized into the carbonyl. So if it's delocalized, it can't act as a base. So that can go up there, or it can go down into that one. These can go in there, or up onto that oxygen. But if we break this down, this nitrogen looks like an amide. And then this center carbonyl, this N, that center carbonyl group, does anyone know what that's called? Huh? What? Azide is N3. This is called a urea. So you have this basically urea type functional group. It kind of looks like a diamide. And then this part is an amide. So nitrogen and carbonyl, that lone pair is always delocalized. So no matter what, it's not really basic. In here we recognize the three sp2 orbitals, so the lone pair is in a p orbital, and therefore that one is the most basic. Questions? So let me, I'll do yellow. So the ones highlighted in yellow are delocalized due to resonance. And then the one in that smaller ring, that's part of an aromatic system. Then this green one, that lone pair is not in resonance. It's just in an sp2 orbital that's just sticking out sort of orthogonal to the pi cloud. And like I said, the ones in the amide and the urea, they have resonance with the carbonyl group. So that's where, again, the nitrogen is acting as a base to do a proton transfer. Yeah.
I don't understand why that one was the most basic.
So this slide is a little bit of a preview. I'll just introduce it now, but it'll become more important in Module 4. But we're going to talk about it now just in terms of NH acidity. So if we have an amine with an NH group, so either primary or secondary, the one shown here is a secondary amine. The pKa of that NH bond is about 40. And so we know that that's a pretty weak acid. But if we want to deprotonate it, we can use a very strong base, and that's called N-butyl lithium. And we can think of it as a carbon anion with a lithium counterion that can abstract that hydrogen. And so now what happens is it puts the two lone pairs on the nitrogen and makes this base called lithium diisopropyl amide. So notice that nitrogen has two lone pairs and a negative charge, so it's much stronger than starting with a neutral amine. And the two isopropyl groups are kind of there to help solubilize this in organic solvent. So this is a strong base. And remember, when I say base, it's only interested in abstracting a hydrogen atom. So another way of describing this is non-nucleophilic. So a nucleophile is when you're forming a bond to carbon. So you can form a strong nitrogen base to do your proton transfer without it doing any SN2 chemistry. Again, the relevance of that will come into play more in Module 4, but since we're talking about amine bases, this is one of the strongest ones you can generate. Any questions before we shift gears here? So that's the structural features based on what the hybridization of the nitrogen is, where the lone pair is, how it acts as a base. But now how do we get nitrogen into a molecule? And so the way we're going to do that is primarily with SN2 chemistry. So nitrogen as a nucleophile. This is your standard SN2 reaction. And the three reagents that you see are the most common sources of introducing N into a molecule. A couple of things to note. They're all salts. So sodium azide, potassium thialimide, and potassium cyanide. Notice with cyanide, the nitrogen is not the nucleophile, it's the carbon. The reason that these reagents exist is because ammonia, which is NH3, ammonia is not really a good nucleophile to introduce nitrogen. What happens is you over-alkylate. So since we're no longer dealing with hydrogen, if we're dealing with carbon, we call it an alkylation. That nitrogen atom will get many carbon groups on it. So for example, if you took ethyl bromide plus ammonia, and you wanted to make ethylamine, the reaction wouldn't stop there. The ethylamine would react again with ethyl bromide to get you diethylamine. Then you would get triethylamine, and then you would get tetraethylamine. So you'd get a pretty big mixture of products from that. And you can't really control it, primarily due to the fact that that lone pair is labile, meaning that it's going to reform and then realkylate. So the thing with all of these reagents here, the sodium azide, potassium phthalimide, and the cyanide, you're masking that lone pair, meaning there's not another lone pair to overalkylate. Yep.
So would that reaction make triethylamine at the end? Like if you just keeps alkylating?
It would make a mixture of them. So you'd get the ethylamine, diethyl, triethyl, and tetraethyl. So it's not going to just stop on the one you want in your mind. You're going to get a distribution of them. And so that's the issue. You just want one compound in the best yield with the highest chemical purity. And so you have to use these masked reagents. And because they're not just making amines, you have to remove the protecting group. So it's usually a two-step process. And we saw from the reactions to make ethers, we could take an alcohol, then make this sulfonate, where this was a good leaving group. And so we can use those as electrophiles and then treat them with any of those three reagents. So you can make an azide, a phthalimide, or a nitrile. And the next couple slides will show you some structures on how to do that. But again, the product you're making, as you see, it's the word azide or phthalimide or nitrile. It's not an amine. So you have to do some other step to make it into an amine. And so we'll start with bromocyclohexane, which is a secondary bromide, so it's fine for SN2. We can treat with sodium azide and DMSO, which is a polar aprotic solvent. And so that's going to do a functional group transformation. So the bromine now becomes the azide. And again, that's not at an amine stage yet, so we're going to reduce it. And we'll use lithium aluminum hydride in THF for that. So that's THF. And now we end up with our primary amine. If you use potassium cyanide, again, the thing with that is it's the carbon atom that's the nucleophile. So we have K plus and then the carbon's bearing the negative charge. So that will displace And now we get the nitrile. So let me just expand that. You see that both the carbon and the nitrogen are at higher oxidation states. So carbon's at 3, nitrogen's also at a higher oxidation state, so we can reduce it. And this would use hydrogen gas, rainy nickel, and methanol. And so ultimately what it's doing, it's taking that oxidation state of the carbon from 3 to 1. So you have that CH2 spacer in the middle. But this still ends up being a primary amine. Questions? So the last of those reagents is the one that actually has a name to it. I'll skip this stuff. This is called the Gabriel amine synthesis. So remember from the ethers, there was the Williamson ether synthesis. This is the Gabriel amine synthesis. And this one uses the potassium thioimide. So the nitrogen with a negative charge has 2 lone pairs now. So you have your normal lone pair and then the extra one, which is giving it the negative charge, and the potassium balances that out. So the solvent is DMF. So that's a polar aprotic solvent, good for SN2. You're substituting the bromide for the thioimide. So notice that word there. An imide so like that's an amide. An imide is basically something with 2 carbonyls bonded to it. The thal means phenyl, so thioimide. So the thioimide is then deprotected with that. Whoops. So that's called hydrazine. You can think of it as like diammonia maybe. So hydrazine ethanol, that removes the imide part, giving you your primary amine. So if you started with the 2-bromopentane and used sodium azide, then reduced it, you would get the same product. Any questions? So that's how you get form primary amines. If you're wondering about secondary or tertiary amines, those reactions are covered in the next module. On this slide, since you're using an SN2 mechanism, you have to use a methyl, a primary, or a secondary substrate for the leaving group. You can't use tertiary because those reagents won't react. So if we focus on this carbon right here, it's a primary amine, but it's bonded to a secondary carbon. What if we wanted to make that carbon more substituted? For example, we can't use this. because it's tertiary. So how do we make amines that have a larger or bulkier group on that carbon? We have to do a different type of reaction. So the next two reactions, maybe what I can point out, and so these are rearrangements. The first one is called the Hoffman rearrangement. And so it's going to start with a primary amide. And then you're going to treat with molecular bromine, Br2, under basic conditions with sodium hydroxide and water. And what you see in the product is basically you're sort of excising or removing that carbonyl group. So this carbon in red immediately gets bonded to the nitrogen. So I won't have time to draw the mechanism. I'll draw what the intermediate is. The mechanism's in your book, you can check that out. But the intermediate that's formed is looks like that. So maybe I'll color this carbon blue. So that carbon basically gets deleted. And then you have this bulkier carbon group. Again, that's only accessible by the Hoffman reaction. You can't use those other reagents to make that. So this thing is called an isocyanate. So a couple questions about that. What is the hybridization of that carbon atom? So it's sp. You have 2 sigma bonds, 2 pi bonds. So sigma, sigma, pi, pi. It's just another way to rearrange that hybridization. Normally you're used to seeing it, in an alkyne, like a triple bond, or a nitrile CN triple bond. And then what is the oxidation state of that carbon? So it's 4. So there's carbon dioxide. That's the highest oxidation state carbon can get. So when you're at oxidation state 4, those make good electrophiles because they want to be reduced. They want to go to 4, to 3, to 2, or 1. So things want to attack them. And the importance of that is when we get into module 5 and we start learning how to make peptide bonds. There's a reagent that looks like this. You have these carbon groups coming off. That's called a carbodiimide. And so it's at oxidation state 4. So really it helps amino acids condense with one another. So that's how, in the lab, that's how chemists make peptide bonds. So your body does it very differently. But these are nice reagents that were figured out basically in the 1950s for the synthesis of antibiotics, which we'll talk a little bit about how you make an amide bond and an antibiotic to do a condensation reaction. So the second type of that rearrangement is called the Curtius. Notice that this is not an amide anymore. See that? That's the N3, that's the azide. This is called an acyl azide. Essentially the same thing is happening. You get the same product, but you're just starting with a different starting material. So the Hoffman and the Curtius, if the side chain is the same, you end up with the same thing. Practically speaking, the difference is, one, you actually have to handle bromine. If you've ever worked with bromine or seen it in a bottle, like if this was filled with bromine, it'd be really heavy. I mean, you'd be surprised at how heavy liquid bromine is. You take the cap off, and this brown fuming smoke of death is coming out towards you. If you imagine like the public swimming pool, but a lot worse. I mean, it's really nasty. So that's a disadvantage of the Hoffman. The Curtius, you have to make that acyl azide. Those are kind of tricky to make. We'll learn more about that in Module 3, but as you see, the reagents are heat and light. I mean, there's light and there's heat in the room. So they can be kind of challenging to work with, so they don't spontaneously do things you don't want them to. But the intermediate's the same. It goes through that isocyanate, and then that carbonyl gets clipped off. Any questions? So now that we've made some amines, what are some of the reactions of them? And again, there's always a blending of these modules, so this does bleed into a little bit about Module 3, which is on the higher oxidation states of carbon. So if we take a primary amine and we react it with an acid chloride, so benzoyl chloride, that carbon is at oxidation state 3. The amine gets acylated. And what we end up with now is a secondary amide. So an amine plus an acid chloride gives you an amide. Yep.
It says only primary and secondary amine can be used.
Yep.
So you can make either secondary or tertiary amide.
Correct.
But you can't use ammonia to make primary amide.
You could use ammonia, yeah.
Oh, okay.
That would work.
Okay.
Again, because see that lone pair now? Because that lone pair is delocalized through resonance, it's no longer nucleophilic.
Okay.
So the reason you can't use, say, a tertiary amine. There's no NH bond. So this would react with the acid chloride, but then it would just go back to the starting materials because you need that NH to do an elimination. So we could say primary amine goes to secondary amide. Secondary amine goes to tertiary amide or ammonia goes to primary amide. I mean, if you're looking at the product, basically the way you split it is right there. So that's your amide bond. And then when we're talking about biological molecules, we call it the peptide bond. So amides of the oxidation state, 3 functional groups, are the ones that exhibit the most resonance. So we know from electronegativity that oxygen's more electronegative than nitrogen. So that lone pair on the nitrogen can be delocalized onto oxygen. And now you have this charge separation. So O minus N plus. And essentially what that's doing is, when you look at this form, that's a sigma bond, that's a pi bond, but the resonance contributor is a bit more. So now you have pi bond and sigma bond. And that explains why in the IR, amides are less than 1700. Because that carbonyl has more sigma bond character now, so it drops it to the lower wavelength, or the lower wave numbers. So that's again explained on this slide, but a consequence of that, you have your sort of neutral looking amide, then you have this resonance hybrid. Because you have this double bond between carbon and nitrogen now, you can actually get sort of the same thing you have with alkenes. So this geometrical isomerism, cis or trans, and that will affect how the NMR looks. Because you have the C and the N, then the double bond, then you have these 4 substituents. So all 6 of those things are in one plane. And then the NMR, the magnetic environment will matter. So you'll see basically a difference in those substituents. So for example, I drew this molecule DMF, that solvent. If you were to just from a first approximation say how many unique sets of hydrogen are there, you'd probably just say 2. You have this aldehyde H, then these 2 methyls, which are bonded to that same nitrogen. So in a ratio of 1 to 6. Now the resonance form of this the methyl groups are still bonded to the nitrogen, but now they're magnetically inequivalent. So if you're thinking of that as a sigma bond that can freely rotate, these methyl groups should be the same. But now you have this double bond. So that methyl group is on the same side as that oxygen. This one's on the same side of the hydrogen. And really in the NMR, what you do see is 3 signals in a ratio of 1 to 3 to 3. These methyl groups are their own singlets now, 2 separate singlets. Let me see what I'm doing here. Okay. And so this is an example of that isomerism, where now you have different groups. So basically you have, the nitrogen has, the secondary amide, so you have an H, then this 3-carbon propyl chain. So you can have the H and the phenyl on the same side. Or they can be on different sides. If there's a rotation, then the isomers or the resonance. So that rotation requires 90 kilojoules per mole of energy. So what will happen is that you're going to get, say small and large sort of on the same side to exhibit the major hybrid, resonance hybrid. And then you could see those proportions by NMR. So the NMR spectrometers have a temperature thingy on them. You can actually heat the sample. So when you look at this, if you see the two resonance hybrids, if you heat it, you'll get this back and forth and they'll sort of coalesce into one. And again, that property of amides is very important for peptide and protein synthesis. So the naturally occurring amino acids adopt a certain E or Z geometry, and then from that, they'll fold a certain way that gives them their reactivity. So one other thing I want to mention on this slide. We were talking about that secondary amide. It has this resonance form. The amide bond is the strongest oxidation state 3 functional group bond. And because of that, amides are very hard to hydrolyze. And what I mean by that is just break that amide bond. And biologically that's important because the things that do reactions in your cells are proteins. They're made of amide bonds. You don't just want them willy-nilly breaking down. So the proteins are made of that very strong bond. They're able to carry out their function without being hydrolyzed. So another reaction of amines is called sulfonylation. And so these form things called sulfonamides. So notice the end of the word here. There's the word amide, but then we have this sulfon in front. So that's basically this part of the molecule, that little heart-shaped thing. You take an amine plus a sulfonyl chloride, that gets you a sulfonamide. So like amides, sulfonamides are pretty strong to acidic or basic cleavage. The difference between, say, what we learned before that was a sulfonate, and that whole thing was a good leaving group. So when it's a sulfonamide, it's not a good leaving group. Or stated another way, they're more stable than sulfonates.
Is it also because of the resonance?
Yeah, so in the periodic table, you know, you have oxygen and sulfur in the same group. So in the sulfonate, they're sort of better matched. In the sulfonamide, the nitrogen sort of won over. So the sulfonate would have better resonance after it becomes a leaving group. And so now that we know these different functional groups, the amine, the amide, and the sulfonamide, the amine is the least acidic of that NH bond. The amide acidity increases because now you can stabilize it due to resonance. The sulfonamide is the most acidic, so it has a pK of 15, about that of water. So that's a benefit of putting that group on there, is you can increase the acidity of that quite a bit. So why are sulfonamides important? So they're basically the main functional group in sulfa drugs. I don't want to violate any HIPAA, but there's probably someone in here that is very allergic to sulfa drugs. With any population of people, there's usually a few that absolutely cannot take these. So within each of them, you see the sulfonamide, sulfamethoxazole, glimepiride, and sulfasalazine. I think I'm getting that right. They're nice functional groups in medicinal chemistry because the reactions are pretty easy to run. There's a lot of amines, there's a lot of sulfonyl chlorides. You just jam them together and there it is. You test it as a drug. So they, as I said, they do have some nice physical properties. They're more resistant to metabolism. And metabolism is basically, you know, when you take a drug, it goes into your liver, and your liver is oxidizing things to put oxygens on, make it more polar so that your kidneys can excrete it. So when you have these sulfonamides, they're less likely to undergo metabolism and then hydrolysis. Any questions? About 5 minutes left. We're going to use them. As Dave Chappelle says, let's wrap it up. We need to just want to get through this stuff so you're prepared for the exam here. So 2 more reactions real quick. So we've seen how to make this primary amine. So we see that primary amine, we can get it in there through the sodium azide, then reduce, or the Gabriel amine synthesis and deprotect. But what else can we do if we don't want to make an amide or a sulfonamide? Well, you can get rid of it completely and make an alkene. So that nitrogen has a lone pair. if you treat with excess methyl iodide, basically all the hydrogens go away and you're going to polyalkylate the nitrogen. So really it's that amine is reacting with the methyl iodide 3 times, and it's making this salt. And so now that nitrogen is a good leaving group. So you can treat it with this base, silver oxide and water. And it's going to do an E2 reaction. So it's going to eliminate along this backbone here. So this H in that group leaves as trimethylamine. So the rule is basically that when you look at the carbon bearing the amine, the carbons next door, the one with the most hydrogens is the one that undergoes the elimination. You can do that for practice. It will help you on the exam. Okay, I want to get this reaction in before we end here. The last reaction here is called the Cope elimination. So it's taking an amine to an alkene. So just like the other one, except now the conditions are a little bit different. We have a tertiary amine, and we're going to oxidize it with MCPBA. So remember, that's a peroxide. So we have a lone pair. It's attracted to the electrophilic oxygen, and it makes this oxide. And what it's going to do when you heat it, it's going to grab a hydrogen from the beta carbon to do an elimination. So it's going to make an alkene. So I got a minute left. So total beta carbons, there's 3 hydrogens, 2 hydrogens. So this says if the syn elimination occurs from the beta carbon, from C1 beta carbon of the longest chain, what is the name of the product? So this is C1, 2, 3, 4, 5. So 1-pentene. So the lone pair is going to abstract that. This will do the elimination. And then the nitrogen gets a lone pair back. So we're putting the double bond between carbons 1 and 2. I finished in time. Just look back to the slides for any reactions that resemble this stuff. It should help you on the exam. 30 questions, 9 bonus questions due tomorrow at 2:15.